Hi, first of all, a very good evening to whoever has joined. So, I welcome you all to the first tutorial session on the transmission and EM waves course. Hello. So, again, good evening, everyone. So, I welcome you all to the first tutorial session of this course. So as you already know, there are two TAs of for this course. So first tutorial already happened on Saturday, I guess, and this is the second tutorial, and for me it's my first tutorial. So without wasting any time, what I will do, I will share my screen and then can go. Okay, so I guess my screen is visible to everyone. So can you just say yes or no so that I am sure that my screen is audible? Okay, thank you. Okay, again I welcome you all. So this is the first tutorial of the transmission line in EM waves course. So first of all I would like to introduce myself. So my name is Ujjwal Singhal and I am a fifth year PhD student in the Department of Physics, ISC Bangalore, and my research is based on the superconducting qubits where I am trying to make a small scale quantum processor. So in my everyday research life, I am mostly dealing with the microwaves or transmission lines and some more stuff. So uh, okay, then let's go forward. So first, I would like to mention like what you have covered in week 1 and week 2 course. So as you know, like tomorrow you have to submit one of the two assignments, like assignment 1 and assignment 2 have a due date of tomorrow. So what I will do here, uh, just, so what I will do here first, I will mostly discussing some of the problems from the week 1, week 2 and some from the week 3, like they will cover the all stuff, and you may have solved some of the problems in the earlier tutorials. So I planned this tutorial so that no question is same as that tutorial. So mostly we will be discussing some new problems. So this is just a recap. So what you have learned in week 1 and week 2. So first of all, you learn like why one need to understand the transmission line theory when you are dealing with the high frequency or microwave circuits or the signals which have very small wavelengths. So you have already discussed transmission line theory, and from that you have also discussed like what are the telegraph equations, wave equations, and then we move on to solving the Laplace equation by using the finite element method, and then we see like how the voltage on a transmission line propagate. So voltage on a transmission line can form a standing wave which can have a forward and backward direction, and therefore we define the reflection coefficient, and then we move on to discuss the bounce diagram of some of the circuits. So this was the briefly outline of week 1, week 2 and some from the week 3. So and right now I want to discuss like what will be our workflow for the tutorials. So for sure we will be solving some of the practice problems. So as you need to submit your assignment tomorrow, so I will not be discussing the assignment problem from the week 1 and week 2 assignments. But what I will do in the next tutorials, I will be first discussing these two assignments solutions or answer. Like if any one of you have problem in the solving the assignment, then I can discuss them or the answers in the next tutorial session. So basically we will be first discussing the assignment 1 and assignment 2 in the next week, and then we'll be solving some of the problems which will be based on the week 3 tutorial. And then I would also discuss like some of the questions which I find on the discussion forum. So basically if you have any doubt, so like within some lecture you can post it on the discussion forum, and from there what I can do, I can pick the questions. Either I can reply there or I will reply by here in the session itself. Okay, so this will be our workflow for the tutorials. So as I mentioned, today I can't discuss the exact problems from the week 1 and week 2. So what I will do, I will discuss some new problems which can help you in solving either week 1, week 2 or week 3 tutorials. Okay, so as I discussed, so these two questions I found on the discussion forum. So there was one question like one person is asking, so what are the prerequisite of this course? So either we need to have some knowledge of the electromagnetic waves or not. So I will say no, it does not require any EM theory knowledge, because as we go more deeper, like in the course, you will see that we will start with the Maxwell equation. So you don't need any prior knowledge of the electromagnetic theory. So basically, if you don't know some principles of EM theory, then it's okay, because we will be discussing it in future. Secondly, there was one question which was based on the octave simulation, where we try to solve the telegrapher equation or the waves on the transmission line. So the question is like, I don't see any boundary condition implementing in the code. So yeah, correct, there is no boundary condition imposed, and because as we start first by creating a current and voltage matrices, and we assign the zero values to all the current and voltages, and in the for loop we are excluding the boundaries, right? So if we are excluding the boundaries, then the what code is solving within the, like, it's not solving on the boundaries but is solving in the middle. So basically your boundaries is always at zero potential. So this was the second thing. So now this we will keep discussing as we have more question, and I will be keep you updated either in the discussion forum, or we will be I will discuss the questions here. So what I will do now, we will start with some of the problems. So here it can be some problem from the week 3. So what I will do, I will show you the problems, and then I will wait for some time, and I would like you to solve the problems so that you can get more benefit from them. So here I will show you the problem 1, and then I would like you to answer in the chat box. And then so this is because let's make the session very interactive. It's not that I come and just solve the problems and you listen and go. So I would like you to solve the problems. So here is the first problem. So we have a 75 ohm coaxial transmission line, so which has a length of 20 centimeter, and the load impedance at the end of a transmission line is has real plus imaginary part. So real part is the resistance, this is the reactance, and also it has a dielectric constant of 2.56 at f is equal to 3 gigahertz frequency. So there are three parts of this problem. So one is the first you need to calculate like what is the input impedance. So what is the input impedance that is seen by the transmission line. Secondly, you need to calculate what is the reflection coefficient at the load. So you need to calculate the reflection coefficient at L is equal to 20 centimeter. So what is the reflection coefficient there? And third, find the reflection coefficient at the input. So basically at L is equal to 0, you need to calculate the reflection coefficient. So I will wait for like some time, and maybe if you don't want to solve, maybe you can give a hint in the chat box, like what we will be using in order to solve the problem, or how do we approach this problem. So I will wait for it, and I will see if anyone responds in the chat box, and then I will discuss the solution of this. Okay, so I think question is clear. So you have a transmission line which has a 20 centimeter length, and the characteristic impedance of that line is 75 ohm, and at the end of it you have a load impedance which has both real and imaginary part, and also it has some dielectric because it's a coaxial line, right? So coaxial line has central as well as the outer conductor. So between the in and out, like center conductor and the outside boundary, there is some dielectric, which is basically Teflon, because Teflon has a dielectric constant of around 2.56 at 3 gigahertz. So now you need to find like what is the input impedance of this, and some reflection coefficient which is at the L is equal to 20 centimeter and at L is equal to 0. So okay, I am waiting for your answers. So let's see if anyone responds. So if anyone know how to approach it, then she can answer. Mm, okay, I will wait for 1 or 2 minutes more. So I think if someone is solving or not, I don't know, but I will wait. Okay, I don't see any answer. So what I will do, I think I will go forward and try to solve this problem. And one thing, I don't have the pen, so what I have done, or any writing device, so what I have done, I have already prepared the solution and I have put it as a JPG image. So we will be going through that to see what is the solution. Okay, so what I will do, I will start with the part A. So first of all, if there is air only, then phase velocity will in medium will be just speed of light, right? So but now, as I said, so there is one dielectric constant. So what dielectric constant will do? It will slow down the phase velocity. So phase velocity in any medium can be written as c divided by the square root of the dielectric constant. Okay, so as you know, c is 3 into 10 power 8. So from there you can easily calculate like what is the phase velocity, right? This is easy. So basically you just divided the c by the dielectric constant and you will get the phase velocity. Now one can go on and one can actually calculate like what is the phase constant. So we know beta, which is phase constant, is 2 pi by lambda, which has a unit of radian per meter, right? And lambda can be defined as Vp by f, where Vp is the phase velocity and f is the frequency. So if you go to the problem, you see you have frequency and you also now know the phase velocity, right? So one can go on and calculate like what is the phase constant of this. So I can plug in the values. So f is 3 into 10 power 9, because f given here is 3 gigahertz, right? So it is, so it will be 2 pi f, so 2 pi into 3 into 10 power 9 and divided by the phase velocity, which is 1.875 into 10 power 8, because there is a medium, so the phase velocity has slowed down. And from there you can calculate the beta, which will have a this value and radian per meter, right? Now what you have studied, so because the voltage and current always vary on the transmission line, so there will be some input impedance that will be dependent on the length, right? So where you want to find the input impedance. So here what I have written, the general formula for the input impedance, like what is seen by the transmission line. So you can go through your notes also, so you will find the same formula. So the input impedance as a function of L can be written as Z0, which is the characteristic impedance of the line, times ZL plus iota Z0 times 10 beta L, right? So beta L is the electrical length, which you have also gone understand in the course. So beta L is the electrical length, Z0 is the characteristic impedance, ZL is the load impedance. So what I can do here now, you know beta, right? And you also know L is 20 centimeter. Okay, so what you can do now, you know this formula and you know beta, so and you know beta L also, and ZL and Z0. So all the quantities are defined here, right? So there is no variable here. Z0 you know, ZL you know, Z0 you know, beta L you know, right? So what we can do, we can go forward and we can plug in the value. So first of all, as you know, beta we have already calculated, which is 60 pi upon 1.875, and L is 20 centimeter, because the beta has a unit of radian per meter, so L will be 0.2 meter, right? So from here I can calculate like what is the value of beta L. What is the value of beta L? So tan beta L is 3.08. Okay, so you can plug in the value of beta L and you can convert it to degree or radian, whatever you want, and you can calculate the value of tan beta L. And from there you can now plug the value. So you know Z0 is 75 and the load impedance is 37.5 plus iota times 75 plus iota times Z0 times tan beta L. So tan beta L here is 3.08. So from here I think it's very easy to solve. So what will be the input impedance? So if one solves such problem, you will get input impedance of this kind. So for this question, the input impedance is 58.7 minus iota 103.7 ohm. Okay, so the input impedance has what? Both real and imaginary part. So this was the first problem. So this is how you will solve this problem if one is asking you to solve the input impedance of the transmission line. So one will use this formula. So now let's move on to the second part. So now what the question is asking, find the reflection coefficient at the load. Okay, so you know what will be the reflection coefficient. So reflection coefficient at the load will be ZL minus Z0 upon ZL plus Z0, right? So here you can write the reflection coefficient, which will be ZL minus Z0 upon ZL plus Z0. So now from here you can plug in the value of ZL, which is 37.5 plus iota times 75 and minus 75, which is the Z0. And from here again it's a easy problem. So from here you can calculate what is the reflection coefficient at the load. So if you just remember these formulas like input impedance, what is the input impedance, what is the formula, and what is the reflection coefficient at the load. Similarly, if I come to the third part is asking find the reflection coefficient at the input, right? So reflection coefficient at the input will be Zn minus Z0. So basically you will ask like what is the input impedance of the transmission line, right? So from here what you can do, you can calculate the uh, uh, reflection coefficient at the input, which will be nothing but Zn, which we already calculated, minus Z0 upon Zn plus Z0. Okay, so in order to solve this third part, you need to have a prior knowledge of the answer of the first part, which is the input impedance. So from here, if you see, the input impedance which we calculated was around 58.7 minus iota times 103.7 ohm, and from there I can just plug in these values in this equation and I can get the reflection coefficient at the input of the transmission line. Okay, so the input reflection coefficient at the input of the transmission line is nothing but 0.3 minus iota times 0.543 ohm. 0.543. Okay, so this was my first problem. So I hope you got the idea like how should one approach such problem if you have some dielectric constant given and the frequency you are given and some load resistance. Okay, so I hope you got the idea on how to solve such problem. So what I will do, I will move forward, and what we will do now, I want to discuss some of the problems which are based on the bounce diagram. So uh, what I will do first, I will just give you a brief introduction of how we draw the how the voltage and reflection coefficient formulas are written on this given circuit, and then we'll be move on to solve some of the problems which will be based on the bound diagram. Okay, so here one circuit is shown. So here it's a transmission line which is a characteristic impedance Z0, and then at the end there is some load impedance which is equal to RL, right? So here Z is equal to 0 and the transmission line has length L. Okay, and now you connect a battery through it which has some internal resistance Rg, right? And at t is equal to 0, switch is closed. Okay, so first of all, the fact one can ask like what will be the value of the voltage at Z is equal to 0 after you close the switch, right? So first of all, here the fact that the battery has some internal resistance, so there will be the voltage divide, so voltage will divide, right? So here the if I ask, like, first let's go through all of this. So first is what is the transit time? So transit time will be just L upon CD, right, where C is the speed. Second, now one can ask, like, what is the value of the forward moving voltage, so at this Z is equal to 0. So as I told you, because there is a some internal resistance of the battery, so you can basically voltage will divide now, so you can basically use this formula, so to find like what will be the voltage here when you have some internal resistance of the battery. And you can clearly see, if suppose Rg is 0, so basically it has no internal resistance, then whole of the voltage will of the battery will appear here, right? Secondly, you can ask, like, what is the reflection coefficient at the load. So reflection coefficient at the load again will be RL minus Z naught upon RL plus Z naught. And similarly, you can say what is the uh, reflection coefficient here, like at this Z is equal to 0 here. So here it will be Rg minus Z naught upon Rg plus Z naught. Okay, so these are some of the formulas which will be using in the future problems which I will be discussing now. Okay. So again, from this concept, we can move forward and one can actually draw what will be the bounce diagram of this. So first of all, on the y-axis there are the transit time. So this is the same nomenclature which has been discussed in the class. So you have uh, tau g here and tau l are the different reflection coefficient at the input and at the boundary. Okay, so at t is equal to 0, you already know you have V plus voltage appearing here, right? And which will be less than the V naught because battery has some internal resistance. Okay, so now what will happen? It will take one transit time t to reach this boundary, right? So you start with V plus and then you move on to the boundary which take one transit time. So voltage here will be V plus. Now this boundary has the reflection coefficient of tau L. So what will happen? The reflected voltage which is moving in the backward direction will have value tau L times V plus, right? And now what will happen? Now in the second transit time you will again come back to the starting point, and from there you again have some reflection coefficient which has value tau g. So what will happen? The uh, forward moving wave after reflecting from this boundary will be tau l times tau g times v plus, right? And similarly you can go on and then you can keep calculating like what are the voltage as you go more in time, right? Okay, and one more thing which sir discussed in the class. So basically what you are doing, you are basically you can basically divide them into zone. So basically if I draw some like line here, vertical line, and if someone is asking you like what is the voltage with respect to time at some particular position z, right? So what you learned in class, so basically when you move down you basically keep adding the voltage, right? So if I am in this zone, right, so I have a zero voltage, but when I am in this zone this whole thing will have V plus, right? Now if I am in this zone, third zone, so the voltage here will be 1 V plus plus tau L V plus, so it will be 1 plus tau L V plus. Similarly you can go down and then you can keep adding the voltage and you can calculate like what will be the voltage at some z with respect to time. Okay, so this is a basic concept of the bounce diagram. Now what I will do, I will show you some of the problems, and on the basis of that we will be solving 2 to 3 problems on the bounce diagram. Okay, so this is the first problem. So here I have a V naught is equal to 4 volt battery. Okay, and it has some internal resistance of 225 ohm. Okay, and then the input impedance of the transmission line is given as 75 ohm, and also the transit time of this transmission line is given as 1 nanosecond, and the load impedance is also given, right? So first of all you want to draw like what is the bounce diagram of this. So I will again wait for some time and I would like you to draw the bounce diagram for this circuit. Okay, or I can yeah, please try to solve this problem. I will wait for 1 to 2 minutes. I hope you understand the problem, because this is the similar problem which I discussed in detail in like earlier slide. So here I have just put the values, and I want you to solve the first. So there will be three parts of this problem. So first part is to draw the just the bounce diagram of the this circuit. Okay. So I am waiting. Does anyone able to draw the bounce diagram of this? You can go up to maybe 6-7 transit time. So I can give you hints. So first you calculate like what is the voltage which will appear here after just closing the circuit, and that will be V plus, right? And then you can calculate what are the two reflection coefficient at the boundary as well as the here that is equal to 0, and from there you can easily calculate like what will be the bounce diagram of this. So please try to solve this problem. RL is 25 ohm. I will wait for more time. I want you to solve this problem because it's a good problem, and you will get like similar questions will be in assignment. So it will be good if you can, because I will be going forward. We will be solving some of the problem which will be based on this. Let me know if anyone uh, drew that. I can also show you the formulas if you want. So these are the formulas. You just need to put the values. T is already given, which is 1 nanosecond. Z naught is given. V naught is given. RG is given. ZL is given. Everything is given. I will wait for 2 minutes more, and then I will discuss. Okay, so yeah, does anyone able to solve this problem? No? Okay, so what I will do, I will show you the solution and you can compare your answer with that. Okay, I will go through the solution. Okay, so first of all, one can ask like t is already given, like t is 1 nanosecond. Z naught is for this problem is 75 ohm, right? So and Rg is 225 ohm. So if I find the value of V plus, like what will be the voltage appearing here, like from where I need to start at t is equal to 0, right? So Z naught is 75, Rg is 225, Z naught is again 75. So what value it will be? It will be 1 volt, right? Because Z naught is 75 and Rg is again 225, and 225 plus 75 will be how much? 300. And then if V naught is 4 volts, so V plus. Okay, so basically you had to start from 1 volt here, right? Now what you need, you have now answer like what is the value at t is equal to 0 on the starting of the transmission line, right? But now you need again two things. First of all, you need the reflection coefficient at the end point and reflection coefficient at the starting point, and then you can keep them multiplying, right? So basically the reflection coefficient at the load, so it will be RL minus Z naught upon RL plus Z naught. So if I calculate this by putting the value, I will get tau L is equal to minus half. Okay, and similarly I can calculate the reflection coefficient at the starting point, so it will be half. Okay, so I can write here tau g is equal to half and tau L is equal to minus half. Okay, now what you can do, as you know, in the one transit time the 1 volt will reach the end point, so it takes 1 nanosecond to reach it from starting point to the end of the transmission line. So here you can just draw the transmission line arrow from 0 to 1, which has a value of 1 volt. Now as I told you, what you need to do now, it will get reflected from here and the value will be tau L times the value which is coming here. So tau L times 1 volt will be minus half. Okay, so it has a value of minus half volt. And now again you travel back, and at t is equal to 2 second, now you have come to the starting point, and that also has some reflection coefficient, right? So that will be again multiplied, so you will getting minus half times 1 by half, so that will be minus 1 by 4. Okay, and again now you can go beyond that, and when you reaches t is equal to 3 nanosecond, again you have come to the end load end. So again you multiply it, like minus 1 by 4 will again get multiplied with minus half, so you will get 1 by 8 volt. Okay, and then you can keep going, right? So 1 by 8 multiplied by 1 by 2 will be 1 by 16, and then you will again at t is equal to 5 nanosecond you will be again coming to the end of the transmission line, and then you again multiply it with minus half, so it will be minus 1 by 32, and then it will be minus 1 by 64. So does anyone able to get the right answer of this? No? Okay, great. And also now, as I told you, so you can consider them as a zone. So here the voltage will be 0, and now you go here, so voltage will be 1 volt in whole zone. And then if you go here down, the voltage will be 1 minus half, zero point 0.5 volt all over here. And then if you go here, it will be zero point 0.5 minus 0.25, right? Because it's minus 1 by 4, so this whole region is 0.25 volt. And then you can go down, so 0.25 plus 1 by 8 will be 0.375 volt. And then you go more down, this zone will have 0.375 plus 1 by 16, so it will be minus 0.375 volt. Okay, so this is how you will solve such problems. Okay, so I think it's very easy, like if you just know the concept, I think you can solve any problem which is based on the bounce diagram. Okay, so this was the first part of this problem. Now, yes, yeah, tell. Yeah, So basically, if you see, this is like a geometrical progression series, right? Right, which has a so what you can do, you can write it as a sum, and then you know at when you have an infinite geometric progression, what is the sum of that. So it will be a upon 1 minus r, where a is the first term and then r is the ratio, right? So from there you can calculate like what will be a steady state voltage on this. Okay. Yeah. So now I will give you the second part of this. Okay, so and I want you to solve that problem. So So again, it's the same circuit. Okay, now you need to calculate the voltage on the line at Z is equal to 3L by 4 with time. So what I want you to plot the voltage at Z is equal to 3L by 4 with respect to the transit time. So how will be the voltage profile that will appear on the transmission line at Z is equal to 3L by 4 with respect to time? Okay, did you got the question? Right? Uh, okay, then please solve it. I will be again waiting because I want to I want you to solve the problem. That's what the point of having these tutorials. Or if you don't able to solve it, then you should actually try like whatever you know. On the basis of that, you should actually try so that you can get some input, right? So the problem is very simple. Earlier, you what you did, you plotted, you just draw the bounce diagram, right? And I can tell you, like all the problems which I will be discussing next will be just based on this, which will be solving by using the bounce diagram only. So in this problem, I am just giving you a hint. So the transmission line total length is L, and you need to find the voltage plot with respect to time at Z is equal to 3L by 4. And you have solved such problem in class also. So I want you to solve that. You are solving, right? So I have already given you the hint in the earlier problem also. Like on the basis of zones, you can solve this problem very easily. So please take time. It's time is not a problem, but you should solve this problem. And it's a easy problem, I can say. You just need to plot a voltage. Yeah, I will. So value, yeah, I will keep the slide on this. You can use this and just plot the voltage at Z is equal to 3L by 4 with respect to time. Like how the voltage will appear on Z is equal to 3 by L by 4 if I am seeing in the future, like with respect to time, what will be the values of the voltage at Z is equal to 3L by 4. Anyone got the answer? And it was like same problem sir has also discussed in the class. Anyone? No?
If this is 3L by 4, the voltage will go on adding with time. So 1,
So have you plotted the diagram? Then I can go through the solution and you can again check like whoever has solved like whether it's a correct answer. If it's not a correct answer, then you should understand the mistake and just learn from that. Have you drawn that? Should I go to the solution or should I wait? If someone is solving, I can wait more, no problem. Okay, I think no one is solving that, or can someone reply like if anyone has solved? Or you can say no also like not able to solve, then also I can go beyond and discuss the solution.
yes, I was trying, but actually I got confused.
Okay, then I will tell you like how to solve, but learn, and then in future if you see such problems it will be really easy. Okay, I will go and discuss the solution. Okay, so first of all, as you know, you should understand like as I told you, these are the zones, and here it's zero voltage, and then you cross one boundary, you have 1 volt, then you cross minus half boundary, you have zero point 0.5 volt, and you keep adding it in the zone as you cross these boundaries, right? So what will we do if I ask you like what is where will be the z is equal to 3l by 4? So z is equal to 3l by 4 will be somewhere here, right? Because z is equal to half will be l by 2 will be here in the middle, and 3l by 4 will be 0.75 times l, right? That will be z is equal to 3l by 4. Now what I can do, I can I want to plot that thing in time, right? So what I can do, I can fix my z. Okay, so here is the solution. So what I can do, I need to find the value at z is equal to 3l by 4, right? So what I can do, let me just pointer. So here you can see you need to find that z is equal to 3l by 4, right? So basically your z is constant now, but your time is changing, right? So what you can do, you can just draw the line, right? Some vertical line at that position. Okay, now you know the transit time is 1 second to reach the voltage from starting to the end point, right? But if I ask you how much time it will take to reach 3l by 4, so basically it will be 0.75 nanosecond, right? So basically from 0 to 0.75 nanosecond there will be 0 volt, nothing will come to the z is equal to 3l by 4 because your wave has not reached there, right? So what will happen at this is 0.75 nanosecond, so at 0.75 nanosecond, as I told you, you will have 1 volt, right? So basically when you cross this zone there is 0 volt, and then when you are in this uh, region. So I told you this whole region has 1 volt value, okay. And then if I cross this layer, so total time will be 1.25 nanosecond, right? Because you can calculate it easily, right? So from 0.75 to 1.25 nanosecond, I am within this boundary, right? So the voltage will be 1 volt, right? Now if I go beyond, so I am moving from 1.25 to 2.75 nanosecond, where the wave is again coming from the left hand. So here, as I told you, the voltage is 0.5 volt, right? Because you can just sum them. So from 1.25 nanosecond to 2.75 nanosecond, the voltage will be zero point 0.5 volt. So here you can see it's 0.25 zero point 0.5 volt. And similarly, from 2.75 to 3.25 nanosecond, the voltage will be 0.25 volt. Okay, so from 2.75 nanosecond to 3.25 nanosecond, voltage is 2.25 volt. And again from 3.25 to 4.75 nanosecond, the voltage is 0.375 volt. Okay, so here you can see it's 0.375 volt. And from 4.75 nanosecond to somewhere here, it will be, you can add just 0.5 to it, so it will be 5.25 nanosecond. Yeah, 5.25 nanoseconds, so voltage will be 0.4375. Okay, and you can go and you can take it to infinity like whatever you want. But did you understand the concept, like how to solve this problem? uh, if anyone have doubt, I can go through it once more, but this should be clear, like how to. So once you have the bounce diagram, you can write the what are the voltage in typical zones, right? Did anyone get it correct? Hello, hello, can anyone answer? Let me know please, like if you understand it or not. I can go like 2 more times, 3 more times, but I should get the answer, right? No. So I will go through it once more.
Sir, excuse me.
Yes.
Good evening, sir.
Yes.
Sir, can you explain once again?
Okay, so what I will do, I will go back to this. So you understand the bounce diagram, right?
Yeah, yes, sir. Yes, sir.
So here, this is typically one zone, I can say, right? Again, I can say this is one zone, and I can
Yes,
go on like here it will be 0 volt, here it will be 1 volt, here it will be 1 minus point minus 1 by 2 zero point 0.5 volt. Then if I go down, zero point 0.5 minus 1 by 4 will be 0.25. So you can go on and you can draw this bounce diagram. So you understand this, right?
yes, sir. Yes, sir.
Okay, so now you
Sir,
see.
just let me clarify. So when we start, sir, it starts with 0 volt, and after 1 nanoseconds, it is one volt when it reaches the load, right?
Yeah, but here also, like here, if I draw z is equal to 0.75, right? So
Yes,
here,
sir.
like here the question is asking z is equal to 3L by 4, right? So 1 second it takes it to travel to the other end, right? But if I say you how much time it will take to travel to maybe half a length, so it will take half a second, right?
Yes, yes, sir.
So basically it's a math. So if I am saying what will be the voltage at z is equal to 3L by 4. So what is 3L by 4? It is 75% of the total length L, right?
Yes, sir.
So it will take basically 75% of the total transit time. So
Yes, sir.
total transit time is 1 nanosecond. So basically at 0.75 nanosecond, that voltage will appear at z is equal to 3L by 4, right?
Yes, sir. Yes, sir.
Now, as I told you, you need your z is constant now, but you just need to plot it with respect to voltage, right? So what
Yes,
you
sir.
do, if you want to make the position constant, so you will draw this vertical line, right? So at this
Yes,
vertical line, z is constant, but your transit time is increasing as you are going down, right?
yes, sir.
And as I told you, so if I ask you like now label these points which are marked with gray, right? So this will be 0.75 nanosecond, right? And
Yes,
now
sir.
if I ask you after reflecting from the load end, at what other time it will reach it? So after, again at 1.25 nanosecond it will come at z is equal to 3 L by 4, right?
Yes, sir.
And then you can go beyond and then you can ask after how much time again it will come to the same position. So basically it will it like at 0.75 nanosecond it will come again. After reflection from the right end at 1.25 nanosecond it will again come back. and then it will go backward, it will reflect from the starting end, and again it will come back, it will total be 2.75 nanosecond. Okay, then you can basically label these all times, right? So basically now you know the times, so now you can say, so till 0 to 0.75, right? So there is zero voltage, right? And from 0.75 to 1.25 you are in this zone and you have 1 volt, right?
So we are calculating at the length, the voltage at length 0.75,
Yeah,
not
but
dot length. So
yeah.
the voltage at that point will be 0 initially.
Oh no, why 0? Because your V plus is always 1 volt, right? It's not 0 volt. Why? Like from 0 to 0.75 nanosecond, it will be 0 for sure because voltage wave has not come, right? So here you can see this is 0.75 nanosecond. So from 0.75 nanosecond to 1.25 nanosecond, you are in this boundary, right? Whole. So it will be 1 volt. Okay. Now from 1.25 nanosecond to 2.75 nanosecond, you are in this boundary, and the voltage here is 0.5 volt, right? So your diagram will be from 1.25 it will drop to 0.5 volt and it will be keep going till 2.75 nanosecond, right? And from 2.75 nanosecond to 3.25 nanosecond you are in this region and the voltage is 0.25 volt, and then so you have this 0.25 volt, right? And then you can ask like what is the voltage again from 3.25 to 4.75 nanosecond, so it is 0.375 volt, and then you can keep drawing it, right? So
Sir, what my question is, only the voltage is changing at the ends, either at the load end or at the start end.
yeah, yeah, but this you are drawing with respect to time, so with respect to time your wave is traveling, right? So at the same position you will have different
But
voltage.
it gives a wave of 1 volt.
Yeah,
At the low, it is reaching to be 1 volt.
yeah, but it will again reflect, right? Because it has a reflection
Even
coefficient.
when it reflects, it is decreasing to something like 0.5 volts.
Yeah,
When it
my
is reaching,
yeah,
it is retaining 0.5 volts.
yeah,
Whatever may be the distance.
yeah,
That's what
yeah, yeah.
I understand, sir.
Okay, you got it. Okay,
Yes, sir. Yes, sir.
so now you, I hope you can solve such problems, right? Because it's really easy. Okay, so now this was the second
Excuse
part.
me, sir.
Yes.
Sir, please once again repeat the problem, sir. 3 by 4 we have to calculate the time.
Okay,
Voltage.
so I can again start. So first of all you draw the bounce diagram, okay, that you draw, right? Bounce diagram of this circuit. uh,
Yes, sir. That concept is clear, sir.
okay,
When
so
we have the voltage 1 volt from 0 to 1 nanosecond, 1 nanosecond to 2 nanosecond, that voltage is minus 1 by 2 volt.
yeah, right, in yeah, right.
So the graph is drawn from 1 volt to zero point 0.5. Then again 2 nanosecond to 3, the graph is shown minus 1 by 4, so 0.25. 1 by 8 is
No,
0.125, so we have to add. So 0.25 plus 0.125. Is it correct, sir?
no. So let me again go through it once more. Okay, so basically here this is bounce diagram. I will go here. So here if I ask you within just so within this region, right, if I ask you in this region the voltage is 0 volt, right? Because it has not reached, right? So uh, let's start with this. So here the problem is asking to draw the voltage on the line at Z is equal to 3L by 4. Okay, so the total length of the transmission line is L, and you, the question is asking like what is the voltage at Z is equal to 3L by 4. First of all, if I ask you like how much time it will take from the voltage starting from this end to reach Z is equal to 3L by 4, so it will be 0.75 nanosecond, right? Because if a wave travel L distance in 1 nanosecond, how much it will travel 3L by 4? How much time it will take to travel 3L by 4? It will be 0.75 nanosecond, right? Uh,
Yes, sir.
so here I have marked 0.75 nanosecond. Now you can again say after what time it will again come back to Z is equal to 3L by 4. So first of all you need to see the Z here is constant. So you are plotting V 3L by 4 with respect to time. So basically you are always seeing the one point, and then you are seeing like what are the voltage values of voltage when I am going in time, right? Okay, so first of all if I now you know at t is equal to 0.75 nanosecond only voltage will be 1 volt. Okay, but before that the wave has not even reached, so voltage will be 0 here, right? So at 0.75 nanosecond the voltage is 1 volt. Okay, now here if I ask you like so it will be 0.75 nanosecond to 1.25 nanosecond, so this is 1.25 nanosecond. Okay, and now from 1.25 nanosecond to 2.75 nanosecond the total voltage is 0.5 volt. Okay, so basically this is 1.25 nanosecond and this is 2.75 nanosecond, so voltage is 0.5 volt because the total voltage here is 0.5 volt. Now you can again go from 2.75 to 3.25, so between this region the voltage is 0.25 volt. So basically from 2.75 to 3.25 voltage is 0.25 volt, and then you can go beyond. Did you got the answer? Like how?
Yes, sir.
Okay, okay. So I hope this is clear, and actually this is important. Okay, so this problem you will find in assignment or it can come like anywhere, but it's important. Like okay, so now I will go beyond and I will ask you one more question on this. Okay, so now I'm asking, calculate the voltage on the line at t is equal to 3.75 nanosecond with respect to z. Okay, so now I am saying I am seeing just t is equal to 3.75 nanosecond. So I want at t is equal to 3.75 nanosecond, what will be the voltage distribution on the whole transmission line? You got the question? Okay, so earlier the z was constant and time was changing. In this question, time is constant and voltage position is changing. So basically, your axis will be z, okay, and y axis will be voltage. So please take your time and try to solve this problem where you need to plot the voltage at t is equal to 3.75 nanosecond with respect to the z, which is basically the total length of transmission line. Okay, so I am again keeping my slide on this what do you say, this bounce diagram, because I told you you will be only like you can solve such problem only after you have drawn the bounce diagram. So if you have the bounce diagram you can clearly answer all the problems which are based on this such types. Okay, so again I am waiting. So I want you to draw the voltage at t is equal to 3.75 nanosecond with respect to the z. Okay.
Sir, is it 0.375 volt?
Okay, let's see. But you need to draw a graph. Okay, so it will not be same across whole transmission line, right? So
Draw, you can draw a horizontal line at the time 3.75 nanoseconds between 3 and 4 in the bouncer diagram.
okay, uh,
And it will come between 3 points and 4, the voltage in the bouncer diagram is 0.375.
okay. So you have solved. We will see the answer. I will wait for a few more people. So I want them also to solve, and then you can cross check your answer. Okay. Okay, I will wait for some more time. So question is really simple. It's really simpler than which I ask you to draw at different time and at the same position. So here, if you got the idea of previous problem, this is really straightforward. So basically you need to keep the time constant and you need to plot it with respect to the z, which is basically the length of transmission line. So basically at some instantaneous time you are asking like how is the voltage distribution on my transmission line at this instant of time. So this is the question, and answer is really based on the bounce diagram. So I'll wait for 1-2 minutes more and then I will discuss this problem. Okay, so I hope like few people, I want everyone to solve, but I hope many people have solved. So I will go through the solution and please try to see where you have made the mistake and try to learn from that. Okay, so as I told you, we want to calculate the voltage at t is equal to 3.75 nanosecond, right, with respect to the z coordinate. Okay, so first of all, when I ask you like you draw at constant z but different time, right? So you draw vertical line, but now I am saying you to draw at constant time but different voltage. So what you will do, you will draw a line, a horizontal line at the time value of 3.75 nanoseconds. So if I draw the line at t is equal to 3.75 nanoseconds, so it will be between 3 and 4 nanosecond, and much closer to the 4 nanoseconds. So this will be the my line which I draw. Now as I told you, you just need to see in which boundary you are. Okay, so if I see, so from 0 to this, which will be L by 4, right? Because from time you can see how much it's, so from 0 to L by 4 it will be 0.25 volt, right? Because you are in this boundary. Okay, I hope you got the idea, because in 3.75 nanosecond you will cross L by 4 boundary. Okay, basically you are at the quarter wavelength from the left hand, right? So basically it is L by 4 and you have the value 0.25 volt here. Now if you cross this boundary, the voltage here is 0.375 volt. So basically you have 0.25 volt at L by 4, and from L by 4 to L you have just 0.375 volt. Okay, so does anyone got it right? So one person solved this problem and she was saying 0.375 volt. Did you get it correct? Okay, so you got the idea like how to solve such problem. Like anyone else can ask now, like please draw the voltage distribution of transmission line at t is equal to suppose 2 nanosecond, or so if I ask like in this, draw the voltage as t is equal to 2 nanoseconds, so it will be constant voltage which will be of 0.5 volt, right? And the fact that I ask you 3.75 nanosecond, because now it will cross this boundary and you are in this boundary, so voltage will be different. So basically you switch from, so basically 0 to L by 4 it's 0.25 volt, and from L by 4 to L it is 0.375 volt. And the fact that this, the region you are crossing, it's moving backwards, so your whole wavefront is moving to the left. Okay, so this is basically a snapshot. So if someone take the snapshot at t is equal to 3.75 nanosecond, what is the voltage distribution, then he or she will capture such wavefront. Okay, and similar thing happens here. So basically you are seeing things in the time domain, right? So basically one can actually use oscilloscope, because you know oscilloscope can show you signal in the time domain. So basically one can actually connect a transmission line, pass some signal, and see like what trace you get in oscilloscope. Okay, so basically this was with respect to time, and this one is with respect to the length of the transmission line. And one can actually go beyond, and one can prepare more problems on this, like what will be the current, like that. Okay, so I hope now everyone will be able to solve such problem which are based on bounce diagram. And the fact that this is a lossless transmission line, so you have 1 volt throughout the transmission line, right? When you are going from t is equal to 0 to 1 nanosecond. Okay, that's why you have 1 volt. So I will wait, and I want anyone, if anyone has any doubt, I can go through it once more, but I want you to just understand this problem. Okay, I will wait for 1 minute, and I will wait if anyone responds, and then I will go to the last problem for this, which is something different. But if someone understands this bounce diagram problems, I think she can solve, like if there is some assignment problem, I think now anyone can draw any voltage distribution with respect to time or with respect to the length of the transmission line. Okay, okay, so I hope everyone understood this problem. So what I will do now, I will move on to the last problem, and again I will wait and I want you to solve that problem. Okay, So consider the following circuit. Okay, so this, you see, this is some complex network. So you can think, so uh, what you need to do for this circuit, this whole circuit, you need to calculate what is the value of input impedance. Okay, so you can see there are so many things. So first of all, you have a transmission line here which has a characteristic impedance of z naught is equal to 1, and then it has length of lambda by 2. Okay, and then you have some capacitor. Okay, and then you again have one transmission line which has impedance of 1.5 ohm, and then the length of that is lambda by 4, and then in series you have some resistance which has value of 2 ohm, and then again you have some transmission line, uh, again you have some transmission line which has z naught is equal to 2, and then that has a length of lambda by 8, and the load resistance across all of this network is given by 1 plus 2 iota. So basically it's a complex impedance which has both real and imaginary part. Now one need to solve what is the input impedance. Okay, so I hope everyone understood the problem. So basically so if you have one transmission line, okay, if I remove whole of this network, so one can actually again put the formula of input impedance, like that is z naught plus times z naught plus zl times tan beta l, like that. Okay, so that is a hint, but I want you to calculate the input impedance of this complex network. So what will be the input impedance seen by the transmission line at this point? Okay, I hope the question is clear. So I'll wait for some time, and then I will go through the solution. Okay, so here in this tutorial I already know, like, you have covered some basic problems in the last tutorial. So I just need to give you some other flavor of the some different problems, like which you can get some complex problem. That's why I took these problems. I think numerical problems you have already done in the last tutorial, where you calculate reflection coefficient and etc etc. So these are some different problems. So this will help you for sure. So again I will repeat the problem. Okay, so question is asking calculate the input impedance for the following circuit. Okay, so you have three transmission lines which have different characteristic impedance, right? And so they basically, this is one transmission line, this is second transmission line, this is the third transmission line, and then these two transmission line are connected by some resistance, and this third transmission line has length of lambda by 8, second transmission line has length of lambda by 4, first transmission line has a length of lambda by 2. Okay, so and the load resistance is 1 plus 2 iota, basically real plus imaginary part, and you need to solve. So again I am giving you a hint. If I remove whole this network, okay, if I remove whole of this network, then you can, I think, easily solve, right? Because you know the formula, Zn is equal to z naught times zl plus iota z naught tan beta l, that formula, because z load will be just a capacitor, right? And then you can solve that. But here it's a complex circuit. How you will solve the input impedance of this circuit? I will wait for 1-2 minutes more, and I will go through the solution. Anyway, this is the last problem, so long problem although, but yeah. I'll wait 2 minutes more. Please try to solve it. It will be good. And if you don't want to solve, just think how to approach the problem. That is also good. Again, just a hint, again I am telling this. If I remove all of this, like after the capacitor, if I remove all of the things, then you can just use this formula, which is Z in Z naught times ZL plus iota Z naught tan beta L. So beta is 2 pi by lambda, and length of transmission line you already know. So this will be some different factor where you can evaluate the value of tan. Okay, and ZL Z naught, everything you know. So for single thing you can calculate easily what will be the input impedance, right? So I want you to calculate the impedance, input impedance for this transmission line. Okay, so again one hint, you can break this question into three parts. Okay, so first of all you solve the right side, then you come to the middle side, and then you come to the left side, and then you can solve. So this was a, I think, more than enough hint. So please try to solve. All the transmission line have different length, lambda by 2, lambda by 4, lambda by 8, and then you have some load resistance, load impedance, which has both real and imaginary part. All the transmission lines have different characteristic impedance, and two transmission line are connected by some resistance, which is 2 ohm, and then one and second transmission line have some capacitance between them to the ground, which is minus J3 iota times 3. Okay, so I hope if anyone has not solved, they must have think how to solve this problem. So what I will do, I will go beyond and try to solve this problem. Okay, so first of all, as I told you, so you forget about all this left network. Okay, starting from here, so just see this transmission line which is at the end. Okay, so I can say like input impedance at this point is suppose Z1, right? I can write, right? So I am hoping that input impedance at this point, these 2 points, is Z1. Okay, so I can write Z1 is, I can draw the circuit again and it will be like this, where I am saying input impedance is Z1. Okay, so now what I can do, I can calculate Z1, okay, first, and then I can move forward. Okay, so let's do that. So again using the same formula, right? So Z1 is Z0 times ZL. Either you can write it as ZL cos beta L plus iota times Z0 sin beta L, or you can divide whole numerator and denominator by cos beta L, and then it will be ZL times ZL plus iota times Z0 times tan beta L upon Z0 plus iota times ZL times tan beta L. Okay, I think this is straightforward, right? And the Z1 is the input impedance. This is the same formula I am using. So basically now if you look here, the load impedance is 1 plus 2 iota, right? So and Z0 is 2 ohm, right? And if you calculate beta L, so beta is 2 pi by lambda, and L is lambda by 8. So if I multiply 2 pi by lambda times lambda by 8, that will be pi by 4, right? So basically the argument on of cos and sine will be pi by 4. So here the ZL is 1 plus 2 iota cos pi by 4 plus 2 iota, because Z0 is again 2, and then you have sine pi by 4 upon 2 times cos pi by 4 plus j times ZL. ZL is again 1 plus 2 iota times sin pi by 4. Okay, this is a straightforward. I just put it the formula and I know all the values here, ZL, Z0 and beta L. So from there I can see my Z1 will be like 8 minus 2j, right? So basically I know what is the input impedance that is seen by the last transmission line. Okay, so now what you can do, you can go one step forward, and now you know the whole circuit. I can replace right side of this by some impedance Z1, right? Because that's the input impedance that is seen by the transmission line. So what I have done here, I have just replaced this section, whole section, by some impedance Z1 by calculating the effective impedance here. So that is 8 minus J2. Now again you can go one step forward, and now you can say this resistor of 2 ohm and my this network, they this have resistance, so resistance add in series, right? So basically I can get rid of this 2 ohm resistance by just writing Z2 is equal to 2 plus Z1, because this is a resistance, and here it will add to the real part of the impedance Z1. So basically I can write Z2 is equal to 10 minus J2, and I can replace whole this network by then this new impedance, which is tan minus J2. I hope this is clear. Okay, and now I hope you are following like what we will do next. Now what we will do, again we will be taking this end of the transmission line, which is the second end, and we will say suppose this has some input impedance, suppose Z3. Okay, so basically now you have Z3, and then you have some transmission line again which has input impedance of 1.5 ohm and length is equal to lambda by 4, and then the load impedance is 10 minus J2 for this. Okay, okay, now the length here is lambda by 4. Okay, now if you see, if you try to calculate beta L now, so tan beta L will be uh, just beta L, so beta L will be 2 pi by lambda times lambda by 4, so that will be pi by 2. So basically if you come here now, the argument of both and both cos and sine will be pi by 2, and you know that cos pi by 2 is 0, right? So basically if you now calculate what is the input impedance when you have a length of lambda by 4, so that will be z naught square by z load. Okay, so basically I am using the same formula here. So basically z3 will be just z naught square by zl. So z naught square is 1.5 whole square, and then you have z load here of 10 minus 2j. Okay, so basically now I can calculate what is the input, what is the impedance at this point between these whole network. So basically this is my Z3, so which is 0.21 plus iota times 0.043. Okay, so now you can again go forward, and then you can say, oh, I have now calculated like what is the impedance of the whole network which is beyond the first transmission line, and then I know like my total impedance across the right network is just 0.21 plus j times 0.043, right? And now again, as earlier we do, so if you have in series, your impedance gets added, and if you they are in parallel, then you need to use a parallel combination. So basically now you have get this capacitor, and now you have this whole impedance, and they are in parallel connection. And if you recall, like if you have parallel connection, then you need to use a parallel network. So you need to write 1 by Z4 is equal to 1 by this impedance plus 1 by Z3, and from that you can effectively calculate like what is the total impedance when I have these two impedance in parallel. So basically you have Z4 is equal to 0.22 plus J times 0.028. So basically now you know what is the what is the load impedance of this first transmission line, because load impedance is just Z4, right? So now I can go one step beyond, and now you see my whole this big network is just now reduced to this simple thing, right? And I have, so basically it's a transmission line which has z naught is equal to uh, 1 1 ohm, and its length is lambda by 2, and the load impedance across it is just 0.22 plus j times 0.028. Now again you need to use the same formula. So basically now you again know the characteristic impedance, you know the length, you know what is the load impedance. So basically again you calculate tan beta L. So beta is 2 pi by lambda, and L here is lambda by 2, right? So this will be, what is this will be, so 2 pi by lambda times lambda by 2, this will be pi, right? So now you can come again here, and if you put pi, right, so your beta L is pi, so sine pi is 0. So basically this Z1 is just equal to the load impedance. So basically now you have two formulas. So if you have your length is equal to lambda by 4, then input impedance is given by Z0 square upon ZL. But if it has length of just lambda by 2, then your input impedance is just equal to the load impedance, right? So here what I can say, my input impedance which is ZL, which will equal to the load impedance, and this is nothing but 0.22 plus j times 0.028. So basically my input impedance is nothing but 0.22 plus 0.028 times iota. So I hope this problem is clear, and you see we started with a so complex network of transmission line, so where I ask you to solve for the input impedance of this transmission line, right? And you know, just by using a simple concept that you know like how to write the input impedance of a one section of a transmission line, I can actually solve this big network. And if anyone gives you like a section of 10 transmission line, then also you can use the same concept, right? You can break it into many parts, and then you can reduce it to simple, keep reducing it to simple networks, and at the end you can calculate the input impedance. Okay, so uh, uh, this was my last problem. So I hope you guys learn something in this tutorial, and as I said you, I tried to put some different question which was not covered in the first tutorial, and I hope like uh, those problems were numerical, and here you got the little more better idea like how to solve some bouncing diagram problem, or you have some question which is related to the input impedance. Okay, so this was all about this first tutorial. So what I will do in the second tutorial, I just want to highlight that. So first of all, we will be solving some of the problems. So what I will do, I will prepare a solution from the assignment 1 and 2, because our next session will be somewhere again next Tuesday, and before that you will be submitting the assignment 1 and 2, right? So what I will do, I will prepare the solutions of assignment 1 and 2, and in the next tutorial when you come, first I will go through the answers of all the problems which were there, so starting from the assignment 1 and assignment 2, and then you need to submit the assignment 3 by 15 if I am not wrong. So what we will do, we will try to solve some more problems which are related to the assignment 3, so that you can get much more better idea as like we did today. So here I did not cover the assignment 1 and 2 or the problems from it, because I don't have the liberty to actually discuss the same problems which were in assignment. So this time I prepared some or took some new problems so that it can help you to solve some problems. But in the next tutorial, for sure, we will be starting with the first the solutions of assignment 1 and assignment 2, and then we'll be again solving such type of problems which will be similar to the assignment 3 tutorials. Okay, and also again I need to mention, again I'm mentioning, if you have any doubt, I think on site there is a discussion forum, there is a email, my email also, and if you want to have any doubt regarding anything, you can just post it on discussion forum, and I will try to again take the snap of that, and I will discuss like what is the solution to that. Okay, so I
Hello,
hope.
sir.
Hello.
Sir,
Yes.
I missed the previous two sessions, sir. How to got the
No,
classes?
it's actually one session only, right? So let me tell you. So there are basically two TAs, okay, and we are both independent. So basically, uh, she is covering, she is taking tutorial session on Saturdays, and I am taking tutorial sessions on Tuesdays. Okay, so and also there is a recording. So you must have got some public sheet. She has already uploaded the video. You can go through that. So she has uploaded, so that session happened on Saturday. Okay, so you can go through the recording of that, and this also I will put it on the YouTube after like compiling it. So only one session has been gone there, so it's not two session. Okay, so
Sir,
so
is a link available for that YouTube?
yeah, you must have got some public sheet, no?
Is it in the announcement, sir?
I will put it in the discussion forum. Okay, that sounds good. I will put the YouTube link. Okay.
Okay, sir. Okay.
Okay, okay. So I hope I was
Can
able.
you show the last slide of this problem?
Yeah, for sure. Yeah, this is the last slide.
Okay, sir.
Okay. So okay, thank you all of you for joining this session, and I hope I was I was able to solve some of your doubt. Maybe not fully, but I hope you got something from this tutorial. So that what matters. So again, thank you for joining. So I will be again meet you on next Tuesday, and I have already told you what is the plan of that tutorial session. We will be first discussing two assignments, and then we will be solving some of the problems which are again of such types. Okay, so thank you all, thank you for joining, and please feel free to put your doubts in the discussion forum, or you can mail me or anything. Okay, I will be happy to help. Okay, then I will see you all on next Tuesday. Okay,
Thank you, sir. Thank you.
welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.